right, in the last video we went through and created a function to automate the outlier detection and management process. We made that function and we showed how different techniques can take a feature with outliers and turn it into, or we can either remove the rows and how that changes the distribution, or if not removing the rows, we can replace the outliers with a theoretical max, and we showed what that can do in some cases where it creates this extra spike back here. And then we showed what happens if we impute or predict the outlier values based on sklearn's iterative imputer. It lets us keep all the data and replace the values and still keep the distribution, the original distribution that we had, and even make it a little bit less skewed than it was before. What I want to do now is make a function with you that is going to handle outliers based on a DBSCAN cluster from sklearn. Clustering is a common technique. I'm assuming you have a background in this already. I don't have time to go through clustering. If you don't understand it, it's definitely worth taking the time. Go find a good article on Towards Data Science, or I might have another video on my channel. Actually, I do have some on clustering. You could try those as well. However, I want to just dive right in and make this work. So I'm going to create a function here, and I'm going to call this one clean outliers. The other one is called clean outlier. Again, hopefully you can come up with a better name than I can think of here. The reason why I made this one plural is because the advantage of this clustering technique is that it will identify an outlier based not on just one feature like charges, but rather it will look at all the values in the data set and say, okay, we think this is an outlier, but technically it's not when you take into consideration the values of all the other features. Technically that feature, this value is valid after all. And so clustering will look at all of them at once to determine whether the entire row is an outlier, not whether just an individual feature value is an outlier. So it's much more accurate in that sense in truly identifying outliers. The only downside of this technique we're going to implement is that it takes a lot of processing time, and so it can really kill your pipeline if you have a large data set. So there are still use cases for the function we made in the last video when you have tons of data, and it's still a very valid technique. Especially I like this imputation here at the end that we did in the last video, but I'll show you how this technique we use. It'll work for some of our data sets, but not all of them. Anyway, let's go ahead and pass in the data frame. And then in this case, we're not going to pass in the list of features because it's based on all of the features. So that's irrelevant. So let's just use our usual messages here. Set default that to true. We are going to need a couple others that I'm going to talk about as we go along. We're going to add drop %. I'm going to default this to 2%. And then we need a distance measure, and I'm going to default this to Manhattan, which again, I'm assuming you have a bit of an understanding of clustering. Manhattan's good when we have mixed data types that are both categorical and numeric, which is most of our data sets. Euclidean distance is the most common, but that really just applies to normalized numeric data sets where they're all on the same scale. Finally, I'm going to set min samples. That's a feature of the cluster. I'm going to default it to 5, but sometimes we can modify this up or down to make the algorithm run a bit faster if we have larger data sets, so it's worth passing that one through. Oops. All right. So this is going to get a little complicated, but we're going to try to build it and test it as we go along here. But this will definitely be worth your time making this function for your own processes as a data scientist. Anyway, let's import pandas. As usual, we're going to need NumPy, I think. I can't remember with this one, but we will use Seaborn because if message is set to true, I like to give back to the user some images to let them see how the distribution changed. And I didn't do that in this last function, but you might decide after you see how I use Seaborn in this function, you might decide to go back and modify our other cluster function to include it as well. So Seaborn matplotlib.pyplot is PLT. For the clustering, we're going to need from sklearn.cluster, we're going to import DBSCAN. DBSCAN is a great algorithm for mixed data types. Another good one is optics, but optics was supposed to be sklearn's solution to the slowness of DBSCAN. But as I tried optics on my data sets, it was not any faster at all. And I prefer DBSCAN because rather than auto select well, I'll show you as I get there. Anyway, but I just want you to know that this one is another common algorithm that some people like, but I decided against it in this function. All right, first things first, with clustering, we can't have missing data. And so therefore, like we did before, I want to go ahead and create a version of the data set that is already clean. So I'm going to say clean the data set first. And I'm going to, let's start with missing data. So if messages, first of all, let's drop it. So I'm going to say drop NA where axis equals columns. And this is just going to drop any column with missing data. So if you have columns you want to keep that have only a little missing data in it, make sure you handle it before calling this function, because this is just going to drop the entire column, and I don't want to go through the logic in this function to decide how much is too much data to be missing. Anyway, so this will drop the columns, and I think I want to go ahead and give a message when this happens. Let people know the columns had to be dropped. So I'm going to print an F string here, and I'm going to say, let's just say how many columns were dropped due to missing data. So that'll be df shape 0. Let's see, 0. Actually, I need to make this 1 for columns. Shape 1 minus df dot drop, not equals, minus df dot, drop NA, axis equals columns, and this is going to give me dot shape 1. This is going to give me the count. So the original data frame minus the number of columns there are after dropping all those that had missing data. So I'm just going to say that many columns were dropped first due to missing data. So when I run this function and I get that message, that will be a trigger to me to make sure I go and address those missing data issues before I actually run this function. All right, so that'll be good enough for now. Then I go ahead and I drop the columns, so I need them in there when I print this message, and then I can actually drop them afterwards. What's my error message here for? Am I missing? Oh, single quotes inside of double quotes. Doesn't like that. Let me just change these to doubles. There we go. That should go away in just a second. There we go. All right, perfect. Once I drop the columns with missing data, then I'm going to drop the rows. So same thing again. Actually, let's just copy this, make life easier on ourselves. Okay, so instead of columns, I'm going to change this to 0 for rows. And say I can take off the axis columns because it defaults to rows. All right, so shape minus the rows that have missing data dot shape. So actually here I'll say this many columns were dropped. This many rows were dropped due to missing data. And then once again, go ahead and drop NA. In place equals true. Don't need axis equals rows because that's the default. All right, handle missing data. However, I want to go ahead and still address all of the other issues we've already taken care of, like basic data wrangling, binning categories, and then we'll get dummies after that. So let's go ahead and handle those. I'm going to make a copy, df temp, kind of like we did in the last function, df.copy, because I'm going to want to come back to df at the end, as you'll see when we get there. So df temp, and we're going to set this equal to, let's first bin categories using that function we created. Pass in df temp, features equals df temp.columns, set messages to false. Don't want those printing out. Let's run this for basic wrangling. All right. That should be good. So that takes care of sparse categorical values, takes care of other issues. Even though basic wrangling handles missing data in columns, it also addresses single value columns and primary key columns, things like that, that we don't want to include in the cluster analysis. So that's why I'm calling those in here. Finally, let's go ahead and call getDummies, because DBSCAN wants all numeric data. So pd.getDummies dftemp columns. Did I call it columns or features? Let's see here. Oh no, I'm using getDummies. This is not my function. It's theirs. Columns equals. Actually, I don't even need that, because by default it'll just apply it to all categorical columns. All I need is drop first. Okay. So we've got a clean numeric data set now. Last thing is I'm going to standardize the data set, because most distance measures that we use, if we're to change this to Euclidean distance or something else, they're going to be very affected by the scale of each feature. Features with larger scales will have a much bigger, actually technically less. Oh, anyway. Yeah, the scale will affect which features influence the clustering algorithm the most. So always standardize, or I should say normalize. It doesn't have to be standardized. Normalize the data set. So I'll do that right here with, did I import preprocessing? I didn't. I'm going to need from sklearn actually got nothing. It's just sklearn import preprocessing. And then to normalize the data set, it's just going to be, we're going to recreate the data frame, and then pass in preprocessing dot, I like to use a min-max scaler, but honestly it doesn't matter if you were to use standard scaler, that'd be fine too. Whoops. Dot fit transform, pass in dftemp. That scrapes out the columns, so we have to make sure we put the columns back in. That's why I'm making this as a new data frame, kind of like I did with the iterative imputer in the last video. Give it the columns, give the index. All right. I think that's it. So I'm just going to return this so you can see what's happened so far, and go ahead and run this. So clean outliers. I'm going to go ahead and pull in the data set as usual. And then insurance, I'm going to set this equal to clean outliers, pass in df insurance, and I'll leave the rest of them set to the defaults. df insurance.head. All right, let's see how we're doing here. 0 columns were dropped due to missing data, great. 0 rows were dropped due to missing data, great. No missing data. The values, we can see it was dummy coded here, and everything was standardized to a min-max scale. So it is ready for clustering. All right, looks good. I'm just going to come back in here to my function now and keep editing away. So now that we've got a clean data set, what I want to do is calculate the number of outliers based on a range of EPS values. So let me talk about this. Well, I don't have time to go into detail, but epsilon is a parameter of the DBSCAN clustering algorithm that is important to set. However, epsilon really varies based on your data. So the default epsilon value, I think, is 0.5. But let me show you what happens if we just use the default. Let me create a DBSCAN model. I'll call it DB, and I'll set this equal to DBSCAN. And let's go ahead and put in metric equals distance. So we're passing that in when we call the function. The default is Euclidean, but rarely do we have a data set that is all the same data type, all on the same scale. I mean, we do scale it, but still, these are very different, these dummy codes, from the rest of these. And so I like to use Manhattan, but honestly, it varies by data set too. Manhattan's better though when we have discrete values, which is definitely what these are, the dummy codes. But even children, after being standardized, it's not technically discrete, but relative to charges, age, and BMI it is, because it only has one decimal. So anyway, Manhattan I think is a better one in this context, but since it depends dataset to dataset, we're going to make it a metric that gets passed in and used right here. All right, next, let's add in min samples. So I'll set that equal to the parameter we also passed in. The default here is 5, but you could set it up to 10. Once again, it depends on the amount of variance you have in your data set. And I'll show you a little later on where modifying this will make a difference. But for now, I'll leave it to that default. And then lastly, EPS, I'll leave it at 0.5. And now that I've got that, I'm going to make a new column in the original data frame. This is why I made a copy down here, is because I want to put this, I want to go back to my original data set and take features out of that data set based on whether or not the whole, not features, sorry, take rows out of the data set based on the rows being identified as outliers by this DBSCAN model right here. However, I don't want it standardized. I don't want it dummy coded. I want to do that on the original data frame. I want this function to be as independent of everything else as possible. So as a result, the data frame I want to return is not dftemp. It's going to be df, the original one. However, I'm going to add a column called outlier and set that equal to that DB model that I made above. Dot, it has a parameter called, what am I looking for? Labels. This is the cluster that it gets assigned to, and where label is -1, that's going to be the smallest. That's going to be the ones identified as outliers, or the smallest cluster of all this clusters created. So let's actually return df just so you can see what this is doing under the hood here. Labels. Did I spell that wrong? db.label. Oh, what am I doing? I don't need =1 yet. Sorry. This is what happens when I try to talk and write code at the same time. Just put labels in there. Outlier. Come on. What's the problem now? Oh, what we haven't done is fit it. We just created the model. We didn't actually run and fit the model. .fit right there. And then we need to pass into that dftemp. There we go. All right, so what we get here is the outlier column, and we get the label of which cluster each case was assigned to. Now, real quick, let's just plot this so you can see what it looks like. And maybe one way to do that is to plot something like, let's do a, not a reg plot, let's just do a scatter plot of something like data equals df insurance, and let's set x equal to, I don't know, BMI, and y equal to charges. And then to put the outlier as a color, let me look that up quick. All right, it is hue. I always forget whether it's Z or hue. So I'll make this one outlier. Okay, so you can see here how those, wow, it made 15 different groups for us. Wow. So these are all the different clusters that it assigned everyone to, and you don't see them naturally grouping here because I only plotted 2 dimensions, and it built those clusters based on all of the data, on all features. So that's why they don't look nicely grouped. But what's nice is those that were very uncommon, that were the most extreme outliers, get labeled as -1s. Let me show you here. Let's do df insurance.outlier.value counts. There we go. So sure enough, we've actually got 17, or is it 0-based, 18 different clusters that were created in this. And that's not counting -1. These 65, these were considered as outliers based on a combination of all features all at once. So I just wanted you to see what labels was doing for us. It's the assigned cluster from the DBSCAN metric. All right, so now that we've got labels, all we need to do is filter out and get rid of those that were -1s. So that's easy enough to do. we're just going to drop rows that are outliers. And to do that, we'll just say df equals df outlier equals -1. And that'll do it. So now, when we run this, let's go ahead and run all the way through. Oh, I did the reverse. It only kept those that are -1. I did that same thing before too. Not equal -1. That's what we needed. Okay, so here's our value counts. We've got everything but the -1s. All right, so if this is all we wanted to do, then job done. Really nice. We've got the function made. It'll automatically drop rows based on those that are outliers for us. However, it won't always identify outliers the way you want them to. In this case, it dropped a total of 65. In fact, let's give ourselves a message so we know exactly what happened here. Let's have a, it'll have to be before I drop them. So if messages, undo that, let's print the total number of outliers. So I'm just going to copy this and say, grab those where it does equals -1, dot shape 0. I'm going to say rows, or I'll say outlier rows removed from the data frame. So we get that as a message. Oh, I missed a, I gotta remember to do double quotes. Okay, 65 outlier rows removed from the data frame. Got our message. What though? Watch if we put something like a 3 here for epsilon. Watch what happens. I don't think we need this one anymore. I'm going to get rid of that. And I don't think we need this one anymore either. All right, 0 outlier rows removed. There was only one. The DBSCAN cluster returned only one label, 0. And that was it. That's because the epsilon was set very high, making the required... Epsilon controls how far apart the clusters need to be in order for them to be identified as clusters. And basically, none of the rows were far enough apart based on an epsilon of 3 to identify any of them as outliers. Well, the problem with that is every data set's different. If we run this same function on another one with 3, actually let me go back to 0.5 like it was, and let's run some other data sets in here. Let's do the, let's see, let's grab the NBA, Airbnb, and the airline. So I'm going to make this one the NBA. And this one, Airbnb. So I'll remove that. Remove this. Actually, I'll make this one the airline. And then I'll make this one the Airbnb. Okay. Change these names. Whoops, Airbnb. All right. Let's take a look at the NBA here. In this one, it says, so same code, epsilon of 0.5. In that, with a 0.5 epsilon, we got 65 outliers in the insurance data. Yeah, that sounds reasonable to me. However, in the NBA data, 674 outlier rows were removed. Every single row was considered an outlier. Yeah, that's not going to work. Epsilon's way too high. Or way too low, actually. Airline, this one has a huge... well, no, I shouldn't say huge. This one has 1338 records, but there's very few columns. This one has only 467 records, but it has a lot more columns. Airline has even more than the NBA, and it has a lot more rows. And so this one's taking a little while. I don't even want to try it on Airbnb. All right, this one will take way too long. In fact, I'm going to comment that out just so I don't accidentally try to, there we go, run that one later on. So I'm going to stop this one because even this one's taking forever. Oh, I'm going to have to pause and let that finish. All right. Finally, my keyboard interrupt worked there. That one was just taking too long. Clear that out. All right. So basically what we need is a way to allow them to adjust the epsilon, which that's not a problem. I mean, we could just make that a parameter up here, but I think we can do better. What if instead of saying fiddle with the epsilon until you feel like it's dropping the right amount, what if we just said choose the percent of the data set that you want to mark as outliers, and then let's automatically find the epsilon that drops that amount. That's what I'm getting at here with this drop percent parameter. So the way I want to implement that is increment the epsilon just slightly and find out, maybe keep track of how many records would be dropped. Maybe we start out with an epsilon of 0.01 or something like that. See how many features would be dropped and repeatedly run it in a loop until we get to an epsilon of, I don't know, 10 or 5, or basically go until every record is dropped. And then we can give that feedback back to the user and then let the user decide exactly what percent they want to drop. We can even print out a chart that will show based on different epsilons what the drop percent would be, and then basically give some decision support in helping the user make a choice. So here's how I implemented that in my own function. So first thing, before I calculate this one, I'm going to create a list to keep track of outliers per EPS, per epsilon. And I'll make that a blank list. And then I'm going to start by presetting the total number of outliers to all records. So that would be dftemp.shape. So the total number of rows. I'm going to default epsilon to 0, and then I'm going to create a loop. And maybe let's make this loop a while. And let's simply say outliers greater than 0. And then I want to go through and create a DBSCAN model. And for each value of epsilon, I'll incrementally add a bit more to it and keep track of how many are created each time. So I'm going to say EPS plus equals, let's start with 0.01. So it'll start with a really small epsilon here. Make myself a DBSCAN model. So I'll just copy this, paste that in there, and then rather than set EPS manually, we're going to set it to that EPS variable we just made above here. So it starts at a really low one. I think 0.01 is a safe low one to start with. We don't need to go any lower than that. And then we're just going to add 0.01 to it each time. In samples, distance, okay, that all looks good. We're going to fit the model. And then let's go ahead and calculate the number of outliers. Rather than have to put it in a data frame or something like that, I'm going to use np.count. It's a nice function available in NumPy. Count non-zero db.labels underscore equals -1. So count anything not equal to -1, or sorry, count the number of labels equal to -1. And then let's append that, outliers per EPS dot append that value, outliers. And let's go ahead and print out for now just a temporary message to help us see. I'm going to get rid of this. This isn't going to be anything permanent. But well, maybe we will. If messages, we'll make it an option that they can choose if they want. Print F. And what I want here is to simply give them the number of, well, first of all, let's give them the EPS. So that would be round. I've noticed that Python adds, because of rounding, a lot of decimals to, since EPS is a float, it's going to give it like, I can't remember, 10 decimals or something like that. So I want to round it so it doesn't do that to me. I'll just round it to 2 because that's the number of decimals I'm incrementing by right here. Let's do the EPS, and then let's do, maybe I'll put it all, I'm trying to decide. I'll put EPS right there, and then the next one, let's put outliers right here. This will be outliers. And then finally, let's do just what percent of the data set that makes up. Percent. So this will be round outliers divided by, do I have it recorded anywhere? No, I guess not. Just df temp dot shape 0. And I'll round that one to 3 digits. Okay, so as it goes through and tries each of these, I just want it to print out what the EPS is, and you get the idea here. How many outliers and what percent that is. So let's let that run and see if it works before we do anything else here. So let's run this on insurance. Let's see, labels. Oh, I ran .fit right there. Oh, df, it's db.labels. All right. So columns dropped due to missing data, missing rows dropped. Here's what we get. So our initial EPS of 0.01 says that everything's an outlier. 100% of the data, it's basically saying anything more than this tiny distance from each other is going to be an outlier. Well, yeah, the smaller the EPS is, the more it's going to detect as outliers. I may have said that backwards before, but hopefully it's clear now. As we raise EPS slowly, you'll see that it's going to find right here, it found 5 records that were close enough together based on that EPS that it counted those as a cluster, and then everything else is outliers. And as we continually raise that, it kind of raises the threshold where more and more of them are closer and closer together. Here is where we get 2.2% of the data set is marked as outliers. It finds 29 rows that it marks as outliers with an EPS of 0.56. So what I want to do is, after I create this, and it keeps going, by the way, until it says here's the EPS at which no outliers are found whatsoever. So I'm going to generate this for the data set, and then I'm going to find the record or the EPS that gives me the number of outliers I want. So I'm going to have to round this to whatever the percent is that's passed in. Or, I guess I could just let them do up to 3 digits. Do I make the... let's see, yeah. They can put in 3 digits. That doesn't hurt. So let's think through how we want to do that. Let's add some logic right here. After we run this while, then what I want to do is say, let's find the number of, all right, so here's the code you're going to need. It took me a while to put this one together. So this is the number of outliers to be dropped, and this is going to be the min value of outliers. This is that list. Outliers per EPS. And the key is going to equal, I'm going to call a lambda function here. Lambda. And I'm going to say x equals the absolute value of the value in the list minus round the, so let me write this and I'll explain it. Shape 0 times drop percent. There we go. So let's start in the inside here. This is taking the total number of rows in the data frame times the drop percent. So that tells us the total number of rows that we want to be dropped. And it's going to go through each item in this list, which is the number of outliers identified. That's what's going in outliers per EPS, is a list of these number of outliers dropped. So it's going to round the number of outliers time, no, sorry, I'm looking at the wrong one. Here, round the shape, the number of rows to 0, so it gets it in a whole number. And then this number minus the rounded number, it's going to find the one where the absolute value, or the difference between this number and the desired number, is smallest or closest to 0. And it's going to return the index in this list of which number that is. That index then is going to give us an idea of what the epsilon is. You can probably think of a much easier way to do this than I've come up with. For example, rather than make this a list, we could put it in a dictionary and just make every, you know what? I think I like that idea already. Well, yeah, let's no, I've already got this working. This is fine. So you could make this a dictionary instead, and then calculate this number, and then find the key in the dictionary based on, or find the value based on the number of outliers as a key or something like that. Anyway, if you want to just copy me and trust that it works, that's fine too. So the EPS that is desired, the one that I'm going to need, is going to be the one, it's going to be the index. Now, indexes are zero-based integers, so I basically got to multiply the index by the amount that I'm iterating EPS on. So if my index is 1, that means it's this one right here. Or let's say this is the one I want right here. This one would be index 0, 1, 2, 3, 4, 5. So I need to say index plus 1 to get to 6 times my iteration, 0.01. That would give me the EPS of 0.06. So EPS, to get that, I'm going to say equals outliers per EPS dot index, and I need the index of drops. I need to add to that 1 because indexes are zero-based. So that gives me the index, and then multiply that by the 0.01, the same value that I'm using above here to increment the EPS by. All right, I know that was a little conceptual. It might hurt your head a little bit. Hopefully, if you've got some programming experience, you probably understood that just fine. Yeah, I'm going to go on. You might think of another way. If you're struggling to understand that, you might think through another way on your own of how to keep track of what the EPS is for the number of outliers that equals the value that gets passed in right here. All right, so I got my drops, got my EPS. All I'm going to do now is create a new model based on that EPS. I'm going to keep this line right here and change this EPS equal to EPS. So it gets determined right here, set right there, and I'm basically just reusing this variable from previously, and that's just fine. It creates the model based on that, creates the outliers, prints out a message. Here's how many outliers are going to be removed, actually drops the outliers, returns the reduced data set. All right, so we're still going to have a little bit of an issue that I want to resolve. Let me show you. So we run this, we can see, yep, it's printing everything out, and it shows 29 outliers because when we called it, we left it to the default of drop equals 2%. So basically we didn't overwrite that. Let me just drop percent equals 0.03. Let's raise that a little bit and see what it does. All right, so it takes time to go through and run all these, as you can see. Now it dropped 39 outliers. So where's 39 outliers? That is the one right here, because that is the number that is closest to 3%. So it then grabbed the EPS of 54, calculated the model, and if I were to print out, I may as well print df insurance.shape, we'll see that it's taken out those 39 rows. Okay, perfect. Yep, we've gone from 1338 down to 1299. I went ahead and ran it on the basketball data too. So I want you to see how it worked here and see why we went through all this work. Notice that on this data set, EPS still started at 0.01, but look how much further it had to go to drop everything. It got all the way up to an EPS of 0.422. Compare that to the insurance data set, it never even got over 1. See, this is why it's tough to guess what your EPS is supposed to be. It's easier just to calculate a range of EPS values that give you different amounts of outliers to drop, and instead just let us specify when we call it what percent of the data set we want dropped. Now, depending on this, so I mean, in this case, it calculated a ton of models. We might feel like this could take too long. So for example, if we run this now on the airline data, watch what happens. Man, this one really does take forever. Airline satisfaction. Oh yeah, I had to stop this one before. I don't even want to run that one right now. so many dummy codes that it's creating, I'm sure. That's part of it. When it bins categories right here, yeah, it's going through. You know what I think I need to do on that one? I think I'm going to call basic wrangling. I think that one, let's print out that data frame and see what's going on. I'm going to stop this. Stop. Sometimes when it really gets going, you have to click it a few times and say restart runtime. What I want to do is see if there's a better format for my data cleaning right here for that particular data set. So to do that, I'm actually going to stop the whole function right here and say return dftemp, just so that I can see what that one's doing. So I'm going to come down here, run it. Oh, PD not defined. Did I forget to put that in this function? I thought I did. That's right there. Import pandas as PD. Oh, I got to rerun everything. Run all. I forgot that once I restarted the runtime, down here, the error was on this line. I still didn't have pandas for that one. Okay, here we go. So here's what got created. Let's take a look. Class, gender, that's not too bad. I feel like it didn't create too many dummy codes. Oh, this is the airline data, that's why. Oh, no, yeah, that's the one I was trying to do it with. It's just taking a long time. In fact, I'm going to print out, just as a reminder, dfairline.shape. Oh, this is the one with a ton of data. I was getting it confused with Airbnb. Yeah, I'm going to move this one down. We're going to have to do, 129,000 records. We're going to have to do this one with our prior one at a time method. It's just too much. Let's try this one on the Airbnb data right here. This one doesn't have quite that much. So print df Airbnb. Okay. df Airbnb.head. This is returning. I don't know why I did it in that format. I think we're good. I'm going to go back up here and take this out. Let's not return anymore. Let's let the function work the way it's intended. And down here on this one, I'm going to remind myself not to run that one again. We're going to change this one to clean outlier and just try it on one of the values, but I'll save that for later. Okay, so this is finishing up the NBA data. Takes kind of a long time, right? Because the epsilon had to get so high to drop everything. Airbnb, it's still taking a long time, just on the very first one. Okay, there we go. Epsilon of 0.01. It says everything's an outlier. 100% of the data. Oh, I should change that from percent. I should format this as a percent, shouldn't I? Anyway, look how slow that goes. We can't wait for that. What I want to do is maybe increment the epsilon faster on data sets that are bigger. We can't sit here and wait for it to finally get to 4.22 or whatever it might take to drop everything. So we can fix that. I'm going to stop that one right there. Come on. Yes, cancel. And instead, let's turn this iteration right here into a variable. I'll call it iterator. And I'm going to set this equal to 0.01 and actually use an if block to determine what it should be set to. So I'm going to change this, first of all, everywhere it's used, right there and right here. And now let's just have a simple check of the data frame size. So if df temp.shape 0, if it's less than 500, like our basketball data, iterator, we can keep it nice and small. That's not a problem. elif, and let's just create a few criterion here. And you might think of a better way to do this. I think like a logarithmic transformation would be good. Oh, not iterator, come on, iterator. But you might be able to find some function rather than have to do this if block to make this better. Equals 0. Let's make, oh, so let's move this one up to like 2000. Change this one up to like 0.05. Let's just make a few more of these. So if we get 10,000 or, I don't know, 25,000, let's change this one to 0.2 and maybe this one all the way up to 0.5 or something like that. So you can tweak these to get them just how you like them. But let's go ahead and run it through these again. Oh, once again, I got to run all. Oh, except on the airline. I didn't mean to run that one. It's all right. I'll stop it. Okay. There we go. So this one it jumped up quite a bit here because this one had 1338 rows and we're skipping by 0.05 now. Anyway, that's more realistic. We really didn't need quite as thorough of a, I mean, this one still went through all of them, but at least it was fast. Down here, there we go. So it's still very slow on each model, but as you see on the very first one, it already goes way down to only 94 outliers total, which is only 5% of the database. So maybe I even incremented this one too fast. Maybe I need to tweak this one to be something more like, maybe this one's 0.2, this one's 0.1, or something like that. All right. So I think that's enough for now. This has taken quite a while in this video, and I want to wrap this up. Some suggestions for improvement that you could make. So besides tweaking my little if block here and maybe thinking rather than having an if block, you could make a function where the iterator is some function of the total number of rows so that it skips through or calculates an appropriate number of loops to help with. The other thing that would be kind of nice is we could actually create a chart to display this on. In fact, just to keep things quick and simple, I already have some code for that. I'm just going to copy and paste it in here in case you're interested. What am I getting right here? Did I forget something up in my function? If messages, it's printing that out somewhere, and I've just totally spaced on where it's doing it. Let's see. That one he removed. Printing the data frame twice for some reason here. Oh, right there. I meant to do .shape. That's the problem. And this one's still skipping by 0.5s. I'll fix that. So here's the code that I wanted to share with you that could be useful. Under if messages, besides printing out how many were removed, I'm also going to add a Seaborn line plot and scatter plot. So this is a single dot on there. PLT, do I have that up here? Oh, as PLT. Forgot about that, or messed that up. All right, let's run that now. And now what it'll do for us is print out, oh, iteration is not defined. Did I spell it wrong? Oh, I called it iterator in this one. Let me change these. There we go. Okay, so let me show you what this is doing now. In addition to printing out each of its iterations and each of the models, it gives you a chart and says, here's a dot at the point that you selected. You said you wanted 5% dropped. Here's what 5% looks like. It would be an EPS score of, let's see, this is divide that by 0.5. You could fix my x-axis here, but here's showing you, here's how many outliers it would drop. The reason why I like a curve is this can help you make a decision about what percent to drop. I look for sharp bends where all of a sudden, like right here actually at 12, this might be a better spot. See how there's kind of a little bend right there? That might be a better place to get rid of outliers from here. So 12 divided by 0.05, so like 0.25% or something like that. Let's see how good my guess was. I could probably improve this chart. Oh, I didn't change it much. 11. Right there, it's still taking out 36. Oh, I see, because there's kind of a big jump from here to there. So it would take a bit more. I have to lower this by even more to get it to go down further. Let's try it one more time. No, it's still not enough because 2% is still rounding. closer to this one than it is to that one. I'd have to go down to 1% to get it to drop that far. But see how the chart helps me make that decision a little bit easier? There we go. So 1% means that I drop 9 outlier rows. And this chart does a good job of helping me identify that bend as a good spot. Let's take a look at the NBA data here. So let me put in an amount. Drop percent. Let's set this one equal to 0.05 initially. Oh, and I forgot to format this as percent. That's the other thing I wanted to do. So when I print these out right here, I'm going to multiply this by 100 and then add a percent sign after. There we go. All right, so let's see what we got. This one's a bit more interesting. Everything's an outlier until we get down about here. It found 23 outlier rows. There's only 467 rows total, so I want as few outliers as possible. I think I'd probably go further down and identify 3, 6, 10. Yeah, this one's a little bit tougher, somewhere around here. So I'd probably say only take out something like 2% of that data set. There we go. Now it's formatting this as a percent for us. Oh, I should round it too. One more small thing. Oh, I did round it. What happened here? Round that to 3, but it multiplied by 100. Is that it? All right, let me just add this around there. Multiply this by 100 instead. Take off this one. All right, let's see our chart now. Still 9 outlier rows removed. It moves it down here. Oh, that's a little bit less. So this one, there's not really a clear bend. I mean, there is a bit right there. Maybe, I don't know, maybe right there. Not as helpful on that one. This one is going to be even less helpful on because, well, let's take a look. And then I promise I'll finally stop talking. We'll end this hour-long video here. But hopefully it's been a worthy hour. This is a really cool function to automatically remove the rows based on a much more valid outlier detection method. And you can use this on any data frame. As you see, we're just applying it to everything the same way. All right, I'll pause it while this continues. All right, here's the Airbnb data. Again, because it was so slow and there's so many rows, it only ran 6 models here because it was jumping by 0.2 at a time, which is totally fine. It only had to get to 1.2 to remove everything, or to remove nothing as an outlier. And looking at the chart, I would say this is a nice bend. Either one of these, 2 or 3, these are both nice places to remove rows. This one removes 233. I think that'd be perfectly acceptable. 233 outlier rows out of like whatever that was, 123,000 or something like that. But if you wanted to, you could say, you know what, change it to this one right here and just get rid of, I don't know, something less. So let's see, 3 divided by 0.02, that would be 1.1%. So it would be one of these right here. So I would just change that to drop percent equals, I think that would be roughly 0.1. Sorry, not 0.1. 0.001 is the math I was trying to come up with. Basically, I shouldn't have called this drop percent because I actually used it as a proportion. I didn't convert it to a percent up where I used it. So I should probably rename that. But anyway, I changed it to 0.001 to get me as close as possible to this right here, 23 outliers removed. And that got me all the way up to 4. I would probably peel back on that a bit and go with this one. This is where that second bend is. Make this 0.002. That'd probably be a better one to... I would probably remove those 51. Anyway, either of those are good bends or good places to remove data. All right, we'll call it good here. Hope this was helpful. Next, we'll move on with skewness and then missing data.